so good afternoon, everyone. Welcome to the last lecture in the mini school by Professor Martin Bucher on exploring the cosmic microwave background and the initial conditions of the universe. Sorry, I think I got the title just the other way around. Sorry, Martin. Yeah, I tried to do it out of memory. Yeah, sorry. And this afternoon, after the lecture of Martin, we want to invite you to a social event, and we would like to join us to a pub, yeah, where there are free drinks. And I will share in the chat just now the link where you can access the pub. Yeah, and please join us, and you will have the opportunity to chat to Martin in a more informal environment. Yeah. So Martin, please, you're welcome to. People already know you. They heard you already 3 times. Yeah. So I don't have to introduce you again. You're welcome to start sharing the screen. And maybe while you do that, I remind the participants that last week Martin was in Durban, so he spoke out of Durban. But today he's back in Paris, and that's the reason why we shifted his last lecture, because he was traveling on Tuesday back home. Yeah. So Martin, thank you very much for being with us again. You're welcome to start, and I will share the link for the social event in the chat just now. And please, participants, make use of the Q&A facility or raise your hand, and at the end of the lecture, Ilya will give you the right to speak. Yeah, thank you. Thank you very much. Martin, you're welcome to start.
Okay. Well, thank you for having me. And in this final lecture, which is supposed to sort of talk about the future of the subject, I've decided to shift gear that, and I'm going in dust and grain alignment and polarized foregrounds. And the reason for this is that I thought that it would be good to give you a little of the flavor of some of the difficulties in going the next step with the measurements of the microwave background. So first, let me explain a little and recap a little, the motivation. So we talked about quantum mechanics and inflation, disordering everything, in other words, because H bar is not equal to 0, you with fluctuations of the inflaton field, which is a scalar field that we could explain the density fluctuations, and that these broadly agree with microwave temperature and E-mode polarization observation. And this is a situation should be accompanied by tensor fluctuations, and which are gravity waves, very long gravity waves. And we see these through the B mode, because the B mode should be 0 except for some gravitational lensing. So it's sort of much easier to look there rather than to try to interpret differences in the subtle differences in the shape of spectra that should be non-zero. So this is, as far as cosmology is concerned, one of the future targets of, for a first detection in the CMB of these gravitational waves. And this would substantially strengthen the case for inflation. So here you see the two patterns, and the B mode is, some would say the smoking gun of inflation. Okay, you saw this slide before, and I also showed you this slide of the various microwave background anisotropies, and the blue are the tensor modes, and this is this dark blue pattern is the B mode, and you can sort of see that it slides up and down according to this scalar to tensor ratio that you're trying to measure. And this is a sort of a community now a number of years ago, that in 2014, a team from observing at the South Pole claimed to have detected for the first time B modes that were, they claimed, primordial. And this made the press everywhere. Here is an economist picture, and you can see the aurora at the South Pole. Here's the telescope, and well, a lot of people believed this for a while, and it turned out to be a false alarm, despite an experiment having been done very well, because there are other things in the sky that are polarized. So we saw that previously in our maps, that you could see the galaxy at different frequencies, and that at around 70, you saw most of the CMB, that at lower frequencies, you see galactic synchrotron radiation, and then you see dust at higher frequencies. And let's see, let me just show you a bit the context. So this is a plot from that time, and you could see that, I mean, this almost looks like birds flying above the horizon. These were the various upper limits by various teams, and then these were the bicep measurements, essentially at one frequency. And here you see the L, the multipole number, and you see the expected contribution from lensing. And then this is for a tensor to scale ratio of 0.2. Wait, and they have a lot high points here that sort of suggest that there might be a problem, but they kind of ignored that, and that turned out not to be the problem. And here you see, this is frequency, and then you see the brightness temperature, and this is the CMB, and then you can see various foregrounds. There's synchrotron, which is sort of low frequency foreground where you have cosmic rays electrons that are non-thermal very fast, sort of in the memory that there's this, you know, sweet spot at low frequency. You get better resolution at higher frequencies, and they basically just had one channel. So rather than taking these superpositions and, you know, getting a confirmation and really understanding the polarized dust, they just went on and claimed a detection. So the reason I sort of recount this story is that to highlight how important the foregrounds are, you know, the foreground papers, and understanding all of this sort of dirty astrophysics doesn't get that much attention until something goes wrong. And then people see how important this all is. And I mean, this is an ongoing story. The limits have been on the tensor to scalar ratio have been going down with time, not as fast as one would like. And there's some fantastic experiments planned for the future. But I thought I would focus a little more on the physics of the dust to, you know, give you a flavor of some of what goes into these experiments. Okay, I won't. These are some quotes, and you can see this almost seems like politics. We certainly stand by our results. Then the WMAP people, I wouldn't have held a big press conference about it. And I won't go into this. So let's go, let's talk a little about interstellar dust. So basically, this is a photograph of, you know, sort of the whole sky, and you can see the Milky Way and the dust obscuration. So this would have, I mean, you can see all of this really well in rural South Africa with the naked eye. But so there's a lot of dust out there. And more quantitatively, well, dust primarily scatters light through Rayleigh scattering. So there's this sort of color excess, and you can, you know, compute how much, quote, extinction there is, so you can sort of correct seeing through dust. So this is sort of classic observational astronomy. This is a big deal if you're doing supernovae and stuff like that as standard candles. Here's a dust map. That this is one of the most cited papers in astronomy. So this is from IRAS, and then at higher frequencies or shorter wavelengths from COBE. So this Schlegel, Finkbeiner, and Davis dust map. And you can see that there's basically dust everywhere, but you try to can try to look through the holes in the clouds, so to say, and then you get less contamination from the microwave background. And here you can see these different extinction curves, and, in the infrared, you can sort of see through it, but at shorter wavelengths, you get absorption that is sort of varying. So there are these grains of dust, which is, basically carbon, silicon, oxygen, and iron and nickel, and some other stuff. And those condense into little grains. And if the grains were all spherical, at least for B modes, we wouldn't have to worry about that because it would be unpolarized, so it wouldn't contribute to the polarization. And it turns out, well, the grains are never going to be perfectly spherical, so they're elliptical. So if there's some sort of coherent alignment mechanism, if the dust in the galaxy, then that can cause you problems. So here we're not really interested in absorption, we're interested in emission. And the emission is very inefficient because the grains are too small. So you can sort of think of the grain as being an antenna, and then there's sort of this random electrical noises or fluctuations, and then that radiates. But if you have an elongated grain, well, an antenna that's longer when is more effective in radiating at long wavelengths, so that you get this polarized emission. So it's sort of thermal emission, but at low frequencies, the grains get decoupled. So you get a black body spectrum times something. There's no reason why it should be a precise power law, but the frequency squared is sort of the ansatz that fits the data. Okay, so we're going to go back to, well, almost 70 years to a discovery that starlight is polarized. And that's kind of a bit surprising. You would expect to get some polarization if you could image a star, the center would be unpolarized, and then you would sort of see rings around the center. But then when you average it all away, starlight shouldn't be polarized. But here, the data is this is better, more recent data. You see that there's this coherent alignment. So this is the directions indicated are, where you see higher intensity, so imagine twisting around a linear polarizer. And this you can sort of understand also in terms of scatterers. If you have a needle to be a little exaggerated, well, it's going to scatter light that has the electric polarization along the needle, and the polarization that's perpendicular will not see these little needles. So there were a lot of papers in some of the aspects of interstellar dust and alignment were clarified quite quickly, but there are other aspects that are still not understood today, or at least not completely understood. So where does this alignment come from? Well, it comes from from magnetic fields. So you need some sort of coherent field to tell the dust grains in which direction to align. I mean, if the dust grains are all sort of random, then nothing is going to happen, and it'll all average out to zero. So the goal is to sort of understand the physical processes which underlie this foreground emission, at least for our purposes. So this is a map from Faraday rotation of pulsars, which sort of shows that you have these magnetic fields that sort of follow the spiral structure of the galaxy. Okay, so we can take the black body spectrum, and then we can expand it in terms of an emissivity, and here you have a power law. And there's an interesting argument based on dispersion relations, saying that this power law should be 2 if there are no low frequency resonances, but it's lower than 2. So this is sort of one of the cases where theory breaks down. And the way to understand it is that these grains are not crystals, they're kind of amorphous, and they're being pounded with cosmic rays. So you get all of these sort of lower resonances that give you what appears to be a power law not equal to 2, but if you really think about it, you don't expect there to be any particular power law. And this is an area where there hasn't really been very much theoretical progress. So the theory would say something that is contradicted by the observations, and you can have almost anything. So this is some nice work on amorphous solids. And a lot of this was done by Purcell, who is known, the early work, who's known for his work on NMR most notably. So there were one easy proposal which unless it's alignment. So basically, if you have something with a high mu, it sort of wants to align like a compass needle. But then when people put in the numbers and the temperatures, there just wasn't enough aligning effect, and you would just using thermal fluctuations and statistical mechanics, you wouldn't get anything near the alignment that is required. So that theory was thrown out. And I mean, there's also really not that much alignment around. So basically, if you want to have a lot of alignment, you need, potential based on the orientation, where the difference in the potential energy is much greater than the thermal energy, which would be about 20 Kelvin. That's what you get from the dust temperature. Other mechanisms were required, and one of the things that's kind of surprising is that statistical mechanics sort of fails you here. And when you want to see how statistical mechanics breaks down, you sort of want to look for processes that have different temperatures. So we sort of have a problem with the dust grains getting, misaligned through these sort of random collisions which exert torques. So one solution is to have the dust grains spin very rapidly, much greater, so that, in the rotational degrees of freedom, you would have a much larger amount of energy than K Boltzmann T. And to explain how that might happen, I'm going to sort of give an analogy. So this is sort of a toy that has been much talked about, and I'm very famous physicists have disagreed about how this really works. And what I'm going to tell you, it was one of the theories that with this little toy turned out to be wrong, but was actually is on the right track for dust grains. So here you have this sort of bearing and this radiometer, as it's called, is in a partially evacuated vessel, and one side is silver and the other is black. So if we shine light on it, it spins. And the argument would be, well, if I take a photon and I absorb it, I just get the momentum from the photon. Whereas on the reflecting side, the momentum transfer is twice. So because the photon goes back. So then it should spin around in this direction. So it all sounds very nice, but things don't really work that way. And that was shown by if you evacuate completely, then the thing stops spinning. So this effect is correct, but there's actually a thermal gradient in the recoil from the air, and the difference in temperatures, the thing that drives this around. So I forget what side Maxwell, Einstein, and Reynolds were on, but this is something where clever people can come up with different effects, and in the end, you have to do experiments and calculate the magnitude of everything carefully. But you can sort of see that with a toy like this, there isn't really, you can make it spin very quickly, and with this rotational degree of freedom, cause the something non-thermal. So if you would think of a dust grain, you have ultraviolet light, which has a short wavelength and can sort of be sensitive to the different features. And that can give a torque. Whereas if the temperature has a thermal wavelength that is much larger, then it can radiate isotropically. So you have something almost like a mechanical engine. You have two temperatures, the temperature, the infrared, and the temperature, the ultraviolet, and then operating between these two temperatures, you have something like a mechanical engine. So this is sort of an interesting way to see how you can get the supra thermal rotation, which gives you some sort of stability or insensitivity to these random collisions. In other words, the dust grain can keep its orientation despite the the collation with sort of different shapes, how this might work with dust grains. There are other mechanisms that will give you rotation. One is that you have atomic hydrogen that becomes molecular hydrogen, and then there's a recoil, and this happens on certain sites. And the if the sites are not isotropic, then this will create coherent torques in the frame of the dust grain. Okay, so we're going to talk a little about the dynamics of tops, and this is a photograph of Borenpelli admiring the complexity of a spinning top. Okay, so let's talk a little about the orientation of the angular momentum of the dust grain. And I thought I would to sort of illustrate the physics going on, show you sort of a fiasco US space mission. So this was the Explorer satellite, and you had a rocket that was spinning, you know, sort of like a bullet spins to give it stability. And then there were these whisker antennas that were sticking out. And what happened and could have been predicted is that this rocket spun for a while, as it was supposed to, but then it changed its orientation and was spinning on its side. And we're going to sort of see in terms of very simple physics why this happened, and if the engineers had really sort of looked into this possibility. So the thing to recognize here is that these whisker antennas give you some non-rigidity in the motion, and if you have this thing wobbling, then you can dissipate the rotational energy and into thermal energy. And if the angular momentum is conserved, then the rocket will want to go into a state or align its rotation axis, its body axis, so that it has the largest moment of inertia. So here you see that you have this, moment of inertia like this, and this is very, very small. So for the same angular momentum, you get a huge energy, but then keeping the same angular momentum, which is conserved, I can get a much lower energy by having it spin like this. And you get the same thing happening with dust, and Purcell worked this out and used sort of reasonable elastic moduli and showed that this would happen on a very short time scale. So you sort of learn that the axis of largest moment of inertia. Okay, let's see. I don't want to go too much into the details of this, but it's sort of interesting to work out. Okay, so now we need to couple to the magnetic field. And this is a very interesting experiment done by Barnett about, well, a little over 100 years ago, and where he took these iron rods and rotated them and showed that they, as a result of the rotation, they became magnetized. So if we want to couple to the magnetic field, we need to, not just a spin, but we need a magnetic moment. So how would that magnetic moment come about? And what basically happens is that, well, you have this mechanical, let's see, yeah, I work it out here. You have mechanical angular momentum, but that sort of costs energy. And then you can lower the energy by aligning the spins so that they take up part of the angular momentum. And if you have a paramagnetic substance, then that will lead to a magnetic moment and lower the energy. And this is exactly what happens. And the force that's opposing that is basically entropy. There are a lot more states with zero spin. So even though you would get perfect alignment at absolute zero. Okay, so you only really see this to an appreciable degree with a ferromagnetic substance, because the entropy effect is less. They're very long spins. But if you have very fast rotation velocities, which can sort of get into the gigahertz because of the smallness of the grains, then this can become an appreciable effect. And this is sort of the dual of the Einstein Haas effect, where this is Einstein's only experiment, where you made a torque. So this was measured with a torsion fiber, and we can do the calculation in terms of here is a magnetic, well, this is the bulk rotational angular momentum. So this is just classical statistical mechanics. And then there's the spin, that this is a conserved quantity. And then you can, with very elementary statistical mechanics, figure out how the rotation creates a magnetization. Okay, I won't go. Let's see, I sort of want to, let's see, how much time do I have? Okay, so this, we have something rapidly spinning. It's magnetized, and so it's coupled to the magnetic field, that this isn't really going to give you any useful alignment, because it'll just process but the precession alone doesn't get any net alignment. So you need some sort of dissipation. So the natural hypothesis is that the magnetic susceptibility contains an imaginary part and basic somehow decays. And that all sounded very well, but the problem with that theory was that the time scale was much too long. And then when you put in the numbers, you have these sort of random Brownian motion disaligning effects that are competing. So people looked at all sorts of magnetic inclusions and things like that to save this theory, but it was really quite challenging. And let's see, I think I will go through this a little faster, skipping over some of the details, but you basically get these stochastic models where there's dissipation, and then there's also sort of a white noise required by the fluctuation dissipation theory. Okay, here's some equations. Now let me, if you don't like this theory, here's another theory that I think is very clever, which is from Bruce Strain and Jeremy Weingartner from Princeton. And they suggested that you could have radiative alignment. So forget about the magnetic, that you have starlight that sort of drives these systems around, and then you get this nonlinear dynamics, but then you get the precession in this radiative alignment doesn't require magnetic dissipation. So this is sort of an alternative theory, but this would be very hard to test, because if you just have a simple ellipsoid or spherical grain, you don't have this sort of complicated dynamics. So the radiative alignment is a competing theory. Okay, so these are sort of some of the conclusions, and that understanding how dust grains align is it has a long history, and people sort of thought that this was a solved problem, and within a few years of discovering the polarization of starlight, a lot of the effects were recognized, but new effects were later discovered. There's some new physics that is missing. The other point is that these grains are not regular crystals, but they're likely to be sort of highly amorphous solids. So they're sort of complicated systems that are hard to predict in reproduce in the laboratory. So in the CMB community, there have been basically two approaches to these foreground problems. And let me say that there are other foregrounds, such as at low frequencies, synchrotron emission, which are another interesting subject, but I've just chosen to sort of focus on one of these problems and tell you a little about the dust. But people who come from more the applied mathematics community, well, in part because they don't want to learn the messy interstellar physics, they like blind or data-driven analysis, and they present this as a virtue. Whereas a lot of people from the interstellar medium coming to this subject argue, well, you have to understand the underlying physics, but a lot of it is really messy, and it's kind of hopeless to come up with, very precise predictions. And the level to be subtracted is very substantial. Okay, I wanted to sort of skip ahead. So where is this field now? So this is a slide of some of the present constraints, and the tensor to scalar ratio is, very roughly in the CMB, what is the fraction of the anisotropy that is due to scalars, to tensors to scalars. So that is the tensor to scalar ratio R. In fact, it's sort of defined primordially, so it's a little more complicated than that, and that's off by a factor of, I think, about 3 or so. But here you see various limits. So this is a new Planck compilation, and Keck is a new version of the Keck array, is sort of the next generation of the BICEP 2. Then you have various Planck only, which includes the limits on the polarization. Planck, which is the temperature, which is very model dependent. And then you also have a limit that doesn't use any of the Planck data. So in these sort of combined limits, the advantage that you get is you can constrain some of the parameters, cosmological parameters that give you sort of the lensing background. Okay, so how do you do better? So this is, I'll just show you a slide of, this was something we proposed quite some time ago to do better than Planck. And you have a telescope of roughly the same size, but you have many more detectors. So in this proposal, it was about 100 times as many detectors. And you want a lot of frequencies because of having to get rid of the foregrounds. So you want to show that by taking superpositions that you can get a clean polarized map. And then if you look at the whole sky, whether you can subtract the dirtier regions will, give you confidence whether the data in the cleaner regions is really clean, the quality of the subtraction. So you have lots of frequencies, lots of detectors, and then lots of measures to get rid of systems. The same. So here they have 3 telescopes, and then these there's this shield from the sun, and you also have to radiate away power that you consume in your electronics, and you have solar panels on the other end and something to transmit the information to the ground. So happily, this is something that Japan has decided to go ahead on with international partners from Europe and the United States. And this seems like something that should actually go ahead. So this is the space-based approach where you don't have to look through the atmosphere, but you're very limited by the size of your telescope. So this is 4 meters, which is sort of how big a thing you can get into your rocket. Then there are other competing initiatives like the Simon's Array, which has some South African collaborators to build bigger telescopes from the ground, either from Chile or the South Pole. And those have higher resolution and can also do a lot of useful science with gravitational lensing that something with this aperture size just doesn't have the angular resolution. But both camps claim to be able to do the B modes, and there are different pros and cons. Here you don't have the atmosphere, you have great stability, you can get much higher frequencies to study the dust, but you can't get, you can get maybe order of 10,000 detectors, but not 1 million detectors, which you can get from the ground. That the ground has cannot go into the infrared. It is clear that they can do the foreground subtraction. So there's a lot of other new science to look forward to, not just the lensing in the B mode. There's also Sunyaev-Seldovich effect and clusters. But I thought that in this lecture, I would focus a little on the modes to sort of give you a flavor of some of the difficulty. So one of the major players in this subject said that 90% of the effort goes into doing the last 20 to 30% of the science. And I think that sort of describes the situation, that people basically know how to do these experiments, but it's sort of the scaling up and encountering new obstacles that weren't such a problem in previous experiments, but it should be very exciting to find out if there really were long wavelength gravitational waves from inflation. You know, that would really bolster the case for inflation and would winnow down the space of models that are allowed. And the gravitational lensing is if the CMB is something that should allow one to, for example, normalize other probes. So you have all this in galaxy surveys, problems of bias, but gravitational lensing sort of gives you an absolute measure of the mass fluctuations, and through, you know, cross-correlating the CMB lensing with shells at different redshifts, you should be able to get more value out of different galaxy surveys that go to very large redshift. So that would be one of the arguments. So I think I will stop here to take questions. I mean, in 4 hours, I've only been able to cover a selection of the topics. And thank you for your attention.
Yeah, Martin, thank you very much. It was a fantastic selection of material for the topic. Thank you very much. And I see Yingxue is already up there. Please, Yingxue.
Hello. Yes. Am I audible?
Yeah. Please go ahead.
Okay. So yeah, my question is simple. So you show the spectrum of the dust as a modified black body, which basically a power law multiply with the black body curve. I wonder where that power law come from. How do you derive it?
Well, that was one of my points, that there's no reason for it to be a power law, and a lot of people in the field seem to believe that this is a sort of solid result, that it must be a power law. But going back to the dispersion relation, I can give you sort of an asymptotic low frequency argument. So if you work things out and you assume that you have resonances on the complex plane, the imaginary part representing the decay of the resonance, and there are no resonances, low frequency resonances, then you can do a power series expansion about zero. So obviously, if you had sort of a fractal pattern or self-similar pattern of resonances that pile up at zero, you wouldn't be able to do this power series expansion. And that's how you get the result 2, the power law 2, plus higher order terms. And, you know, the frequency of interest, you observe something well below that. So, you know, we could have certain features of the dust that probably due to the amorphous feature that have, you know, resonance at a certain frequency. So that would be a blip that's not fit by a power law. So power law is just based on what we know, it's an unmotivated fitting function, and may be overthrown by better observations? So it's a good question. And the answer is there's no reason to believe that there's a power law.
And I can see the CAB for cosmic infrared background, which could be a different origin that people also assume like a power law. Maybe the index are different. Do you have any comments on like CAB and the other? I mean, CAB would be another foreground, right? For the, I mean, that would only for temperature, not for polarization, but still another foreground. Yeah.
Well, that's right. So CIB it stands for cosmic infrared background. So background means sort of unresolved sources. And the sort of common understanding of that is that these arise from dusty galaxies. So you have so the physics is quite similar to the dust emission in our galaxy, except star-forming galaxies are sort of much dustier, and you get the dust being heated up by ultraviolet light from young stars, and then it gets re-radiated in the infrared to us. And as Yingxie said, that you know, while this would be, if we could resolve these individual galaxies far, far away, we would see polarization, much like the dust in our galaxy. You get a lot of, when you average over the entire galaxy, since there's no common field, you know, you get their net polarization is zero, absent some mechanism to align their polarizations. So it's principally a sort of Stokes I parameter temperature unpolarized background, but much the same physics.
Sorry, I was muted. No, thank you very much, Martin. Are there further questions from the participants? Be mindful, this is the last lecture in the course, so it's now or never if you want to ask questions. Yeah. But having said that, we promised you an informal chat with Martin at our virtual pub. So if you don't have questions now, I will thank Martin on behalf of all of us. Martin, thank you very much. Those were very nice, interesting series of lectures, and we have recorded them all, and we will make them all accessible. The previous one are already accessible on our YouTube channel, but we will add this one as soon as possible, probably later today. Yeah. So I posted in the chat the link to our social event. So please click on that link before we close Zoom, so that you have it. It should be very simple to log in. I think you just need to register if you haven't never used that website before. Yeah. So I will see you there then in a couple of minutes. Just the time to get out of Zoom and into Kumo space. Yeah. So Martin, thank you very much. I'm looking forward to see you at the pub, and I would be very happy to offer you a virtual glass of a drink of your choice.
Okay.
Thank you, Martin, and thank you, Ilya, for helping with the questions. Thank you very much. Yeah, and thank you to all the participants for being with us for the whole month. And please look in your inbox tomorrow morning. Latest, you should receive the announcement of the next mini school. And that will be a very interesting mini school. In fact, it's the first experiment that we do in mathematics. So we have an introductory mini school to category theory. Yeah, that has many applications across areas of of science. So I hope that some of you will be curious to learn about that next month. Yeah. So thank you very much. I will see you just now in Kumo space. Thank you. Thank you very much. Bye, Martin. Thank you so much.